All right. Mhm. Mhm.
Number went down. I've just arrived here a couple of weeks ago. I'm from Boston. You always stay? Yeah, I told my friends. Yeah, absolutely. Oh, of course. He's the director of the IC. So I was part of the team, I guess. But our kids went to preschool together. We started cooperating. I haven't worked with them yet. So who is your advisor? Get some experience. I'm learning from the different.
Not clear then.
No, it's like
Okay. My name is Alan Riddell. I teach in the Department of Information and Library Science and the Data Science program. It's my great pleasure to welcome you all to this event, and in particular to welcome our speaker, Nathan Sanders. Nathan is going to be speaking about the varied uses of data science in the United States and global entertainment industry. Nathan is Chief Scientist at Warner Media Applied Analytics. Before moving to Warner Media, which I feel I have to remind you was until a few months ago called Time Warner, he did similar work at Legendary Entertainment. Legendary may not be a household name, but the films that it produced, I think certainly are. Films that Legendary produced and Nathan helped market, I presume, include Pacific Rim, Jurassic World, The Great Wall with Matt Damon, and of course, the cinematic triumph, the 2016 movie Warcraft. I mention these films in part to give Nathan a hard time, but also to draw attention to what a complicated and challenging task it is to jointly model critical and financial success of films and of television series. So these two things happen to not be as strongly correlated as you might think. Now, Nathan is a particularly fitting speaker for this series for at least two reasons. First, his work demonstrates how data-intensive quantitative methods are spreading to all corners of economic and cultural life. We are, I think, familiar with how data science is used in e-commerce and the finance industry, but it's less obvious that data science is used to model things like the evaluations of audiences' evaluations of cultural goods and art objects like film. And Nathan's work shows how this is indeed increasingly the case. The second reason, well, Nathan is also remarkable and a fitting speaker for this series because when he stops doing data science for his job, he starts doing data science for the rest of us. He is involved in numerous citizen science projects and organizations. For example, for many years, Nathan has been involved in water quality monitoring for the Mystic River Watershed Association in Boston. And the Mystic River is, after the Charles River, the most important river in Boston for people who live in Boston.
Excuse me, after the Charles River?
The Charles River is a little bit bigger. Is the watershed bigger?
About 500,000 people in the Mystic River.
Okay, it's huge. It's huge. You know, his work there has included developing predictive models for bacteria levels in the river, so they can help people decide whether or not it's safe to go boating or rowing on the river. And I can appreciate this work at a personal level since I grew up in Boston, and I remember a time not too long ago when falling into one of Boston's rivers then heavily polluted, required a trip to the hospital. And it no longer requires a trip to the hospital unless you're a small infant. And then you probably want to go to the hospital anyway. The water quality in Boston has improved enormously thanks to the work of many dedicated volunteers like Nathan, who are engaged in monitoring, data-intensive monitoring of the environment that we all depend on. So for these two reasons and many more beside, I'm very happy to welcome Nathan Sanders to IU. Please join me in welcoming him.
Well, thank you so much, Alan, for the very generous introduction. Not entirely generous, but fairly generous. And thank you to Haishu, Laura, Kayla, everyone at the data science program here. It's such a privilege to be able to visit with you. I'm so excited to share with you some of our work at Warner Media. And I thought I would start off by telling you a little bit about my own career path. Hopefully for many of you, you'll see sort of echoes of your own experiences and goals for the future. And I think it's probably fair to say my path is a little bit unusual. So I started my undergraduate degree in astronomy and astrophysics at Michigan State. So by the way, it's such a treat to be back in the Midwest, and it's really been a pleasure to get to know Bloomington a little bit during my visit. I continued my work as a graduate student doing my PhD at the Center for Astrophysics at Harvard. So I think my career path from astronomy to entertainment is somewhat unusual, but I think it's also entirely representative of what career paths in the modern economy and in data science look like today. I think one of the things that's really exciting about data science is that there's this common set of skills in statistical analysis and quantitative modeling that can be applied to this really remarkable diversity of different domains. And hopefully some of those links between these different areas will be clear just from my own experience over the course of the talk. So I thought I'd start out by sharing with you a little bit of the work that I did in supernova research, and I'll use that to help frame in parts the work that we do at Warner Media. So my advisor at Harvard was a really wonderful astronomer named Alicia Soderberg. She had just started on the faculty there at the time that I joined, and most of our collaboration together focused on what are called core collapse supernovae. So these explosions are the death state of the most massive stars in the universe. So to simplify a little bit, basically any star more than about 8 times the mass of the sun will end its life in one of these incredibly energetic explosions. They're so energetic and luminous, they can actually, a single star exploding can outshine an entire galaxy, the galaxy of stars that it comes from, for a period of several weeks. So a single star becomes brighter than the hundreds of billions of stars collectively around it. But despite the fact that they're so luminous, they're very difficult to study observationally. And the main reason is that they're relatively infrequent. So even a big galaxy like ours, the Milky Way, will only produce about one supernova every century or so. So if we want to study them in like a graduate student lifetime, like collect a population and sample them in just a few years, we have to survey a very large volume of the universe. We have to look at very distant galaxies, often galaxies that are literally halfway across the observable universe, meaning billions of light years away. So let me show you what that looks like in practice. It may not be as dramatic as you might hope or expect, but here's a good example. What you're seeing on the top right is a color image that actually contains an exploding star within that white box. Not easy to see, But if you do very precise alignment between images taken at different times, so the bottom left is basically before and an after image of a host galaxy. If you do a very careful alignment and then a subtraction of those images, you can actually discover an exploding star, as is shown on the bottom right there. So really what we're looking at is a variation in the brightness of that host galaxy by, in some cases, just a few percent or even less. But it has, within that very small variation of this incredibly dim object in the sky, is incredibly precious information to astronomers about how this very important process in our universe works. And of course, that's what we want to study in more detail. So this presents all sorts of really interesting statistical challenges. Namely, if you have an object that's as difficult to observe as these exploding stars are, and you end up with data sets that are very sparse, meaning that you don't get as many observations as you'd like to have, and also very noisy, meaning that the uncertainty of each observation is quite large because there's such dim objects on the sky. How do you study that and how do you understand these objects? So most of the work that's done in this field really relies on extraordinary events, supernovae that just happen to be very, very close by to us in the galaxies in our neighborhood, or supernovae that are so incredibly luminous that we can actually study them in better detail. But that's problematic, of course, because that means we're throwing away most of the information we collect about the dimmer supernovae, and it means that we're getting a biased sample of just these extraordinary events. So the way that I sort of found to contribute to the field was to try and introduce population modeling techniques that allowed us to capture and learn from all of the data that we collect on these supernovae, no matter how sparse and imperfect the observations of any individual object may be. So I want to show you what that model looks like in practice. This is one of the models that we developed during our collaboration. It's a hierarchical Bayesian model, and that has very important implications for the problem I just described. So this model has a lower level structure of parameters that are basically represented by the white circles in this DAG. And those white circles represent the parameters of each individual supernova, its observational properties. But as we were discussing, each individual supernova may not be very well observed, so we can't actually constrain those lower level parameters very well. So we marry that with a joint model for the structure of the population itself. So the higher level parameters here, basically the colored circles, model the population of supernovae. And by modeling the population, we can inform our understanding of each individual object. And by simultaneously modeling the individual objects, we can learn about what the population looks like. We do both together. So here's what that looks like in terms of the actual data. Each one of these plots is just showing you the brightness of the exploding star on the y-axis over time. And as we were discussing, you can see that there's very few points on each of these plots, so we don't get a lot of observations of each supernova. And the error bars here are relatively large, so each observation we do get tends to be noisy. But we can still understand the likely observational characteristics of each supernova quite well. And the reason is that we're pooling information from the population. So each model that's fitted here, represented by the red solid lines, are samples from our posterior individual realizations of our model. Each one is informed by that understanding of the broader population. And even having just a few observations on an object informs our learning of the population parameters as well. So why do we do all this? The reason is really to understand the physical processes behind the supernova explosion, why a star explodes, and which types of stars produce which types of explosions. So ultimately what we do is we measure the bulk observational characteristics of each object, like the total energy emitted by the supernova, which is on the y-axis here, and the kind of the time scale or lifetime of the supernova, which is on the x-axis. And we compare that to simulation models, computer simulations of how a star explodes, motivated by physical first principles. And by comparing the observations to the models, we can infer the physical properties of the star that exploded. We can figure out its mass, its chemical composition, and more. So this will be the last to talk about astronomy, but I will try and weave in some of these same topics about statistical modeling, uncertainty, and statistical inference as I describe our work at Warner Media. So as Alan said, after I finished my PhD, I went to Legendary Entertainment. And again, thank you, Alan, for the mostly generous introduction to Legendary. It really is a remarkable company. And for me, the reason it's so exciting to join at the time that I did was that Legendary was founded by a really visionary CEO, a guy named Thomas Tull. And his vision for the company was for Legendary to be the first studio in Hollywood that was using data and evidence to inform its decision-making about content and audiences. So using data to actually drive the business, which obviously has just pervaded our economy, especially in recent years. But at that time and in this industry, it was really very, very novel. And as a scientist, that was incredibly exciting. So a lot of the work that I've done in the past, I think a lot of the work in science in general, tends to be necessarily incremental. There's a field of research that a dozen brilliant scientists have done great work in already. And your goal as a scientist is to improve that, to move the ball forward a bit, to build on the work that others have done. And that's incredibly important. But I think often as scientists, what we're always looking for is more of an exploratory space where if we're lucky, we can find something that we can apply methods to, like quantitative methods to for the first time, where there's not a lot of prior art or prior work. And that allows us to, I think, make the biggest advancements and the highest impact. So I think for a scientist, it's always exciting when you identify an area where you can really bring your skill set to bear for the first time. And for all of us who are involved in starting this group at Legendary, that was really the exciting part about it and the promise, and why we found it such a rewarding experience over many years. As Alan mentioned, we have recently changed hands. So our Applied Analytics division that was founded and incubated within Legendary was actually stripped out and acquired by Warner Media just earlier this year. So now this will be the only animation I have in my slides. So despite the fact that I'm from a movie company, so you'll have to savor this. Very exciting. Here we go. So now we're part of Warner Media. And as Alan said, Warner Media is a remarkable company as well, and it's undergone quite a transformation in very recent months. So Warner Media used to be called Time Warner. Time Warner as a brand, I think, is well known, but a lot of people, myself included, may not have been familiar with the actual composition of that company, what's actually part of it. So the short story is that Time Warner, now Warner Media, is basically composed of three big operating divisions: HBO, the cable network; Warner Brothers, the film studio and TV studio; and Turner, which operates a variety of different television networks. And Warner Media itself, the reason the name was changed is that it was acquired by AT&T. So now Warner Media and AT&T together are arguably the world's largest entertainment company. And so you can imagine that for all of us who have been working in this industry at our Applied Analytics group in Boston over several years, having the opportunity now to work within this much larger company and this really exciting, pivotal moment in our industry that's changing so much in this era is really exciting. So I'll show you some of the ways that we use data to impact that business. Just a little bit more about what's actually involved in Warner Media. These are all the individual, a subset of all the individual brands under the Warner Media emblem. So hopefully there's a lot of brands here that you interact with on a daily or weekly basis, and hopefully some that you really love. So within Warner Brothers, there's the film studio, there's a games division that makes all the Harry Potter and Batman video games. All of the DC Entertainment properties are wholly owned by and produced by Warner Brothers. There's New Line Cinema as well, and some other smaller wholly owned subsidiary studios. Within Turner, there's lots of great television networks like TNT, TBS, CNN, Cartoon Network, a variety of different streaming services, including Boomerang. Warner Media is also a part owner of Hulu. And then within HBO, there's HBO itself, the streaming service HBO Go, and Cinemax. So again, having just joined Warner Media, we're really excited about the opportunity to work with and support this wide range of businesses, and also to learn from the really diverse parts of the entertainment industry that are reflected across the company. So I want to share with you a little bit about our Applied Analytics division, which is based in Boston. The full mission statement's up here, but basically the way I would summarize what our division does is that we understand and model consumers and content. So on the consumer side, that means understanding consumer behavior, why people make the decisions they do to purchase products, and what influences that decision making. On the content side, what makes a movie or a TV property or video game, other entertainment products successful, what makes it good in a critical sense, what makes it successful financially, what makes it appeal to an audience. And then of course, it's the intersection of those two things that we ultimately really care about. We understand how consumer preferences and behaviors interact with our industry, with content. So that's, broadly speaking, our mandate. So within the Applied Analytics division, we have several teams that all contribute to this effort and all interact with data science. We have a development team of software engineers that do really remarkable work building infrastructure to house, manage, and make our data queryable and searchable, and also build software products on top of that. We have a services division that's composed of analysts and strategists that deeply integrate with all of the brands I showed you on the previous slide and make sure that all of our work directly impacts and is used by and is successful for all of those businesses. And then we have the quantitative team at Warner Media, which is where I come in, the team that I lead. Our quantitative team is composed of a great group of scientists from a variety of different domains. We've worked really hard to have a very interdisciplinary group that spans all of the physical, social, and computational sciences. But broadly speaking, we cluster into a few different categories. So we have a group of primary research scientists. Their job is to interact with consumers directly. And there's several different ways that we do that. So one is by just asking people to report their preferences, their opinions, and their behaviors. So just directly surveying people through online methods especially. Second is to use more implicit measures to develop experiments by which people will reveal their preferences. So often that will take the form of biometric or physiological measurement. for example, doing eye tracking or facial recognition studies on consumers as they watch our films, with consent, of course. And thirdly, crowdsourcing. So actually asking consumers around the country and around the world to perform small tasks for us to help our data science enterprise, to label data or to help us assign structure to data that we can use to feed into our models. And on the data science side, the work that we do is probably straightforward, and I'll talk about it in more detail in a moment. So I want to show you some examples of modeling applications that we've pursued within our applied analytics group. And I want to frame that by talking about this duality in data science that I think is really important. It informs a lot of our work. And that's the duality between inference and prediction, two aspects of statistical modeling that I think are both incredibly important. So I'll be really precise and define exactly what I mean by that. So this is another DAG that just represents arguably sort of the most basic form of a statistical model. So this is a linear regression model in particular. So the idea is we have some set of indicator variables, independent variables that are, of course, data that's fed into the model. We have a set of outcome variables that we care about that we're trying to model, represented by Y here. Those are connected by the predictions the model makes. So, of course, the model's job is to basically transform those inputs and do a set of outputs that match the outcome data as well as possible. Obviously, this is a supervised modeling example. And the way it does that is by designing a transformation that relies on a set of parameters. So there's this vector beta that represents, broadly speaking, all the parameters that the model has learned to transform the inputs into the outputs. And of course, there's some statistical error and prediction error associated with the model as well. So the next statement I'll make is entirely unremarkable and trivial, but I'll make it anyway, and of course it's important. It's that the predictive aspect of this modeling, the predictions these models generate, are very important to businesses. So being able to generate predictions accurately and efficiently at scale enables lots of business operations in our industry and many others. Nothing controversial about that, surely. So in other words, this part of the model is very important, and I'll give you some concrete examples. So in the science use case, taking the astronomy example, if we're observing and modeling supernovae, we might want to make predictions, for example, about the future brightness of that event. So if we observed a supernova last night and we measured its brightness, how bright is it going to be tomorrow? Can we observe it with our telescope, et cetera? On the industry side, we might want to know if a consumer is going to be interested in our products. So we might want to ask, is Alan actually going to buy a ticket to the next Warcraft movie because he's clearly so excited about it? So obviously these predictive methods have a lot of applications to the business. So I want to show you some specific examples from applied analytics. I don't want to give you kind of an exhaustive tour, so I'll just pick a few kind of representative examples from different areas of statistical techniques that we deploy. So first, network analysis example. We do a lot of work with social media data, and one of the most important aspects of that data is actually the network connections, maybe not surprisingly. So for example, on Twitter, for roughly every tweet a person makes, a real consumer makes, they tend to have about 10 follow relationships. So there's actually much more data in general in the connections between people than in the behavior that they're exhibiting, particularly on that platform. So modeling that and understanding and being able to predict how a consumer's past brand interactions, what they say about the consumer's general interest profile and what types of products or brands they're going to be interested in the future is naturally very valuable to us. Secondly, an example from the image recognition domain. So we do a lot of work leveraging deep learning models and convolutional neural networks to understand the properties of the content that we put out into the world, the image and video content that's so core to our business, how that's actually taken up and shared by consumers online. So we'll, for example, look at the pool of images from, it could be like screenshots from our trailer, fan drawings that people make, memes that people share related to our films before it's released, to understand what type of content is appealing to what type of person. And that can help us make predictions to help us target our advertisements, for example, to make sure that we're displaying relevant content to people that they're likely to actually engage with. And a third example from the natural language processing domain, I mentioned that often follower network connections are more numerous, but of course, if you really want to understand what an individual thinks, you want to listen to what they have to say. So being able to interpret the text of what people post on networks like Twitter or Reddit or in reviews in response to a movie is very important. So one of the sort of most straightforward tasks in this domain is just to do an emotional classification to understand at scale, if millions of people are writing about our films, what they really think of them. So we use a variety of different methods for this, in particular for emotion classification, using attention networks to make predictions and classifications about the text that people are producing. So clearly, in my view, and I think everyone would probably agree, prediction is very important and really instrumental to enabling data science to have an impact on businesses. But I do have a concern. I think sometimes we actually go too far with this side this aspect of modeling. So my concern is that often when people talk about machine learning, they use that term almost synonymously with prediction. And there's really a focus and an emphasis on this aspect of modeling. And again, I do think that's important, but I think it can potentially go too far. So to state that a different way, I think if this is the full view in basic terms of what a model looks like, I think too often, this is the view that we think about, where there's this one aspect of the model that's just overwhelming in its importance in terms of the approach that's taken to modeling data. But there's another aspect of modeling that I think is at least as important, and in the business context, often really critical to extracting value and information from data, and that's the inferential side of a model. So actually learning from a statistical model. So in a colloquial sense, the way I like to define inference is that it's the process by which people can actually extract information by comparing a model to data, the way that we can actually learn and update our own understanding of the system that we're trying to model by looking at the parameters that are estimated during the modeling process. So to go back to those two examples we talked about earlier, what does this mean in concrete terms? So on the science side, the astronomy side, if we use a predictive model to understand the future brightness of a supernova, we might use the inferential aspect of modeling to understand what are the physical properties that produce that explosion. Not just what is it going to look like and what it will look like in the future, but why it's happening that way. What caused that star to explode in the way that it did. And on the industry side, we want to know not only is Alan going to go see the Warcraft movie, but why is he going to go see it? What are the factors that are driving him or another consumer to be interested in that film? And importantly, how can we try and match those two things together? How can we try and improve the outcomes for our films by understanding consumer behavior well enough to entice people to see the films? So if the earlier statement was entirely controversial, I hope this one actually is too, which is to say that inference is extremely important to data science and to having an impact through data in industry. So I want to show you another kind of raft of representative examples of how we deploy inference in our modeling work at Warner Media in that applied analytics. So first of all, we do a lot of inferences about content. We want to understand the properties that we're creating in TV and film and beyond. So one of the ways that we do that is through natural language processing. We'll take textual descriptions of our films and other products, feed them into a natural language processing model. In particular, the example shown here makes use of a particular type of topic model called a partially labeled latent tertiary allocation model. And what this allows us to do is essentially to decompose a property into many constituent thematic elements. So the idea is that we have this kind of unstructured, long, high-dimensional description, textual description of a property, and then we can, through the use of this modeling technique, basically boil that down to a latent representation of a few hundred different thematic topics that are highly interpretable. Each one is related to basically, like, you can think of it like a subgenre that allows us to understand the content of that film and allows us to tie those inferences back to predictive models. So for example, to understand how a consumer's interest in a particular one of these subgenres might impact their interest in a specific film. We also do a lot of inferences about markets in sort of a macroeconomic context. So I think there's another interesting analogy to the supernova work here too, which is that on the supernova research, we have these precious few observations of these very rare events. We want to learn as much as possible from each one. And we need to deploy these types of models that can pool information from across the population and that can model uncertainty very robustly in order to learn from rare events. And we do the same thing in the entertainment industry. So in particular, if we're talking about sort of large scale, high budget blockbuster films, there's really only a handful of those that come out each year. And if you want to narrow down to a particular genre or category of film, there's often maybe just one or two that are coming out each year. And because our market changes so dynamically, there's been such big shifts in the industry over just the past decade alone. Each one of those events gives us really critical new information about how audiences are responding to those films and how they might respond in the future. So we want to use these same types of techniques that are valuable for modeling rare events to understand the dynamics and shifts in our industry. And one last example, we model and understand consumer behavior at the individual level. So one area where this is very important is understanding response to advertisements. So if we have a big new film release coming out, it's likely that, especially if you're in the sort of target audience for the film, you'll probably see a variety of different advertisements. You might see a billboard outside, and then you might see an advertisement on TV, and then you'll get a Google search ad. You might see another TV ad later on. And studios in general are spending enormous amounts of money on this, billions of dollars every year across the industry. So of course, we want to target those advertisements and sequence them to the consumer as efficiently as possible. So one of the ways that we do that is through collecting individual level data on how people are exposed to advertisements for films across the industry and across all of those different channels, from billboards to search ads. And then we collect data on the eventual consumption habits of those same consumers, which movies they actually go see. And we fit models that allow us to sort of disentangle all those effects in terms of the mix of platforms they see advertisements on and the sequencing of those ads, so that we can understand the optimal allocation of advertisements to consumers and optimize our future advertising campaigns. And at the same time, we're making inferences about why people are influenced by certain advertising channels. Okay, so what I just showed is sort of a whirlwind tour of a few different kind of representative areas of modeling. And I thought I would give you a deep dive and kind of drill down into one specific area. And so the area I thought would be interesting is box office projection. So understanding the bulk gross revenue outcomes for films. So this is an area that's really important to us. At the same time, it's not like our primary focus. We definitely spend more time on the sort of individual consumer level modeling side of the spectrum. But I think it's so sort of representative and such an interesting aspect of the industry. I thought it'd be a good example to focus on. Lots of our staff at Applied Analytics have worked on this modeling effort over the years, but I especially want to highlight the contributions of my colleagues Abby Dawson, Ben Lawson, Cece Chu, and Jay Dang on this work. So the box office projection task itself is straightforward, predicting the outcome in terms of revenue for a film, but the uses of that model, the reason why we want to pursue that task, I think is interesting to examine. And to go back to that duality between inference and prediction, I think there are implications on both sides of that spectrum. So on the predictive modeling side, box office projection is useful because it helps us optimize and guide a strategy for the portfolio of films that a studio releases. So whenever a studio releases a film, especially a major kind of blockbuster film, you can basically think of it as a huge financial investment. It literally is that. For a big film, the production and marketing budgets combined can easily eclipse $300 million, sometimes much more. And especially for a smaller studio, like Legendary, for example, even a very successful one is typically only producing a handful of movies a year. So you have these huge bets and you only get to make a few of them. It's not a very diversified strategy by its nature. For Warner Media and Warner Brothers, it's actually a much bigger portfolio, which helps, but still you have these risks associated with portfolio investing. So of course we want to understand the likely outcomes of each film in the portfolio in order to be able to manage and mitigate that risk. There are also direct financial applications of this type of modeling in order to understand, for example, the tax write-offs that might be associated with the success or lack of success of a film. So they're very direct predictive applications of box office prediction modeling. But might not be surprised by the point I want to make next, which is that anticipating the outcome of a film is important, but it's not the whole story. You really need to do more than that to extract as much value as there is to be extracted from this type of box office projection modeling. So the other side of this coin, again, is the inferential side. And there are lots of things that we can do based on the inferences from box office projection modeling that allow us to influence our business. So for example, there's media budget and strategizing. So learning from inferences, learn from models trained to historical data about what types of marketing strategies, what types of platform distributions in terms of where we spend our advertising dollars, and advertising strategies in terms of things like pacing, like when we choose to advertise to consumers before release, how those decisions influence the eventual performance of the film, how that interacts with things like the film's genre or the talent associated with it. We want to be able to optimize audience targeting. So with that information, those same inferences that we might use for media strategizing, what does that mean for individual consumers that we're marketing to? How can we best identify the audience for each individual new film that we're producing? To guide positioning. So what we mean by positioning in the entertainment industry is how we choose to present a product, a film, TV show, etc., to the consumer. So for example, a Batman movie, you might choose to describe that as an action flick. You might choose to center and position the film in terms of its brand value, the fact that everybody knows a character like Batman or Superman. If you wanted to make a stretch, maybe you could call it like a comedy film and emphasize the humor aspects, which some superhero movies recently have chosen to do. Those are all valid positioning decisions. And of course, they have real implications for what type of audience that film is going to appeal to and how successful it'll be in the marketplace. And of course, we want to model and understand that. And then finally, not just with inference, but specifically with the fully Bayesian approach to inference, where you're not only modeling the most likely outcome of a system, but also the full distribution of possibilities, the full distribution of possible values, the probability distribution of the parameters in your model, and the predictive outcome. With fully Bayesian inference, we can do a few additional things. One, we can do a really detailed accounting of uncertainty and risk associated with each of the decisions that we're making in production. And two, we can understand the covariance between these parameters. So for example, things like the production budget and marketing budget for a film historically have tended to be very intertwined. When a studio chooses to spend a lot on making a film, they usually tend to spend a lot on marketing it. And so naturally, there's going to be some correlation in the data that induces some covariance in the posterior. So it's difficult, in other words, to disentangle the strength of those two effects because they so often covary. And if your model doesn't have an understanding of that, you might be misled to favor one over another in a way that's unrealistic. So that aspect of this is very important as well. So the way I'd summarize this large set of inferential impacts of box office projection modeling is to say that if we really want to take action on the basis of this modeling, if we want to extract insights from the modeling process that are actionable and that will actually influence our behavior as a studio, the inferential side is really critical. So much of the decisions that we'll make on the basis of this modeling come from inferences from the model rather than just anticipating the outcome of the film. So I want to show you what this model looks like. And so I'm going to show another DAG here, and intentionally, hopefully it looks a little bit like the model that I showed you earlier in the supernova context. So the modeling that approach that we take to box office projection is another multi-level Bayesian model. And the reason that's valuable in this context is really similar to the reason why it's useful in the supernova population modeling context. So on the astronomy side, it was useful because we had these relatively rare and precious observations of individual events, and we wanted to learn from the larger population of events that we've collectively observed in the past. And similarly for film, of course, every film has its own individual unique characteristics. And because we're an industry that produces a relatively small number of products each year, we get relatively few examples to examine the correlation between those properties and the eventual outcome for the film. So it's really important for us to be able to pool information across those properties, across different films, to learn at the population level. So for example, a set of parameters that we have in this model are related to the genre of the film. And some genres are much more populous than others. We have many more examples of action films, for example, than we do documentaries. And so if we want to understand the importance of a variable like genre to this model, we may not be able to regularize that parameter for each genre individually. We may not have enough examples of documentaries to know if it's really important or if we're just overfitting to a few examples. And so we take this hierarchical modeling approach, which allows us to group parameters and learn from the more populous variables like action films, for example, to be able to better constrain the likely importance of a variable like the documentary genre. And we do that for all the variables that are included in the model. So we do take a linear modeling approach, but we also introduce some complexity by virtue of higher level features. So higher order terms associated with our continuous variables and interactions between variables. So the reason that's important is that this is an alternative to a modeling approach like a tree-based ensemble model, like an XGBoost model, which allows you to express an enormous amount of complexity in the model that you're building, but may be less interpretable. It may be hard to do inference with a model like that because by its tree-based ensemble-based nature, it can be more difficult to attribute a quote-unquote decision that the model is making to a specific attribute of the input film. But with a linear modeling procedure like this, where you're explicitly defining the meaning of each variable, that's more straightforward to do. So it's really sort of a trade-off between expressivity and the interpretability of the model. Okay, so the approach that we take to actually fitting this model, I think, is interesting as well. It's not a straightforward challenge. So although it is a model with sort of a modest scope of parameters, so between all of the variables that we put in and the interactions between those variables, we're talking about a few thousand parameters in total, which is absolutely tractable. We do also want to do fully Bayesian inference on the model. So we don't just want to optimize for the most likely value of each parameter, but we want to infer the full posterior distribution and the joint posterior distribution between all those variables. And that's a much harder challenge. Sampling from that posterior is hard because it's fairly high dimensional, a few thousand parameters, but also because there's a lot of covariance between the parameters, a lot of curvature in the posterior. And that's very challenging for traditional sampling mechanisms like Metropolis Hastings MCMC to do. So the approach that we take is to leverage the gradient information in our model in the posterior and to use Hamiltonian Monte Carlo, which can sort of learn from the trajectory, the gradient associated with each step in the chain to make better guesses about where to jump next. So Hamiltonian Monte Carlo is actually remarkably easy, as many of you may know, to implement, but I think it's actually very hard to implement well and efficiently, such that you can run a model very scalably. But fortunately, we don't have to do that because there's a wonderful team of statisticians and computer scientists that have developed a great framework called STAN that implements both modeling language and very efficient implementations of algorithms like Hamiltonian Monte Carlo that we're able to leverage. So I want to mention the modeling language STAN, which is a probabilistic programming language, because I think it's actually a great language to learn. part of what I think makes it really, really successful is that Stan really borrows a lot from traditional statistical notation. So if you can describe the model that you want to build in mathematical terms, the way that you might if you're writing a paper in LaTeX, you can pretty much use almost exactly the same syntax to write your Stan model. So it's really very quick for a statistician to develop a model and to iterate on it over time. And Stan also has really wonderful implementations of a variety of algorithms and interfaces to a lot of programming languages. In particular, we have a lot of Python users in our shop in applied analytics, and there's a great Python interface to Stan called PyStan, which is developed by our very own Alan Riddell. So we really owe a great debt of gratitude to Alan for the work that he's done to make Stan accessible to data scientists through Python. Okay, so I want to show you some examples of what the outcomes from this model actually look like in terms of both predictions and inferences. So I'll start with the predictive example. So the visualization of this is a little bit boring because it's just the anticipation of box office. The prediction of box office is just a probability distribution. So we have a histogram of the most likely outcomes, the probability distribution of outcomes that we expect for a given film. And again, that's very important for things like understanding the risk associated with the film and for understanding its financial implications. But we can also do other interesting things with that prediction, like integrate it into larger systems for modeling our marketplace. So one of the most sort of interesting decisions that studios have to make is dating decisions, deciding when on the calendar of releases you're going to choose to put out your film. And that has really interesting interactions with competition, competitive effects. So even standing here today in 2018, there are films that other studios have announced, and ours too, out as far as 2022, 2024, many years in advance. And so if we have a new movie coming out, like for example, a certain franchise starring a wizard that has like 5 or 6 future releases already planned, if we want to figure out when that's going to be released, we need to understand what the competitive effects are going to be at different times during the year and at different years into the future, so we can find the optimal time to release our film. And to make that even harder, these studios, us included, will often change the release date. So if something about the film's production changes or the marketplace changes, we might choose to move it from one date to another. And that means that this dating decision is dynamic and needs to be reevaluated all the time. So there are lots of interesting approaches to be taken to this task. Let me show you one approach that we use. We, first of all, need to model the slate itself. So we need to understand the properties of these films that are announced to be released over the next several years. But we're doing that in a very low information environment. So if you look at on the schedule 5 years hence, you might see publicly available information, like for example, there will be an untitled Disney film to be released in August of 2023. And in some cases, that may be literally all the information that's available to the studio. In some cases, especially closer to release, you'll get a lot more information. You might know the talent associated with the film, who the director and the actor is going to be. The genre might be announced. It might be announced that's part of a franchise, like maybe it's the next Batman movie, for example. And using that information, we can start to describe the film in the same way that we would as an input to the box office projection model I showed you earlier. But almost always, we're still missing some data. We don't have all the production data about the film because it either hasn't been announced publicly or in some cases won't have even been decided yet. So the approach that we take to overcome that missing data problem is to use multiple imputation. So we take the variables that we do have for that film and we impute or infer the other missing variables on the basis of the data that we do have. So once we have that model for the sort of distribution of likely parameters of all the films in the coming slate and how they vary with each other, we can feed that directly back into our box office projection model. So now we're sort of combining the accounting that we're making of the uncertainty we have in what each release is going to be and our uncertainty about how that outcome is going to translate, how that construction of the film is going to translate into the distribution of likely outcomes for that film. And taking all that together, what we can do is project the likely box office outcome for the entire slate. So I apologize, this is very small. I tried to cram too much into one slide. But what each line on that plot on the right represents is the week-to-week box office outcome for each upcoming film. So for each film, we're predicting what its opening weekend performance is going to be, and then what it's going to be for subsequent weeks. And that allows us to do a vertical sum across that plot to understand the total gross competition, the likely box office performance of all the other movies in the market at that time. And then we can feed that back into the box office projection model with the characteristics of our target film and understand how those things interact. So we can predict which release date would have the highest predicted performance for our movie. So that's on the predictive side. And so I want to switch gears now and talk about the inferential side of box office projection modeling. So again, one of the most important things that this allows us to do is interpret and understand the causal factors that lead to the success of a film. And as Alan highlighted, one of the aspects in cultural products like this that's really important is audience reception, what people actually think about the film. And that's hopefully related to, but is different than the sort of, if such a thing exists, the absolute quality of the film or what critics might think about the film. But how audiences actually feel about the film, how they consume it is very important and very predictive of its success. So we want to model and understand that very well. So we can decompose our model into these individual predictive factors. We can, for example, make a plot like this that shows the relationship between the audience reception of a film and its likely box office performance. And this is just one example. If I show you this plot for another film, it could actually look quite different. So in particular, this is an example for a type of film that has a relatively strong relationship to audience performance. But there are other types of films, and actually I think horror movies are an interesting example of this, where the relationship with audience reception is much flatter. So the quote unquote quality of the film is actually going to have less to do with its eventual performance because the audience is less sensitive to that or less discriminating on that basis. So having those interactions incorporating this model allows us to distinguish between the importance of this variable to different types of film. Once we have that model for how a film's outcome is related to those causal factors, the properties of the film, especially the properties under our control, we can then optimize for those properties. We can use the model to directly guide our decision-making about a movie's construction. So one of the aspects of that that's really important to us is the marketing spend, how much we spend on advertising the film. So if we have a model that predicts the likely outcome of the film as a function of our bulk media spend, then we can compare that to the costs of varying that parameter. So the blue line here is representing a 1-to-1 relationship, where if you were to spend a $1 on marketing, you would make exactly a $1 back. And of course, we want to be optimizing for the greatest marginal returns. So we want to be spending exactly as many advertising dollars as it takes, such that we no longer get $1 back after we spend. That's a little bit reductive because there's more at play on the revenue side than just the box office revenue, but that's sort of the idea. So the right-hand side is literally just subtracting the blue line from the gray line, basically, so that we can see the marginal return. And looking at the apex of this plot allows us to optimize for the optimal media spend. We can also do this for discrete variables like genre. So this gets to that positioning question. If we have a movie that we believe can legitimately be presented as one of a variety of different genres, or we can emphasize different themes, what's the best one to emphasize? So given the other properties of the movie, which genre is going to appeal most to audiences? So we can use these interpretable variables related to genre to understand the film's likely performance as a function of that choice. So the last point I want to make about inference is that it has this unique property that's really important. Actually, maybe it's not unique, but it's definitely important. And that's that inferences need to be interpreted by people. If we want to learn from the inferential side of a model, it has to be presented in such a way and constructed in such a way that we can actually understand it and make decisions based on it. So whenever we talk about inference, we also need to be thinking about communication. So that's the last thing I wanted to talk about today, the importance that I believe that communication has in science generally, both in academic research and in industry. So I hope this almost goes without saying, but I think maybe it doesn't always. I think communication is actually equally important to scientists, no matter what domain you're in, whether you're in business and academia, or if you're just an interested member of society who may not even be a scientist. I think communicating science is critical to all three of those elements. So if that doesn't seem obvious, I want to make the argument for that. I want to explain why I think that in terms of a few different aspects. So first, why should science as an enterprise in general, why should science care about you communicating? And I think one reason for that is that the public is telling us it's important. So when surveys are done on the general public and people are asked, do you care that scientists are communicating to you? Do you want to know what's being done with your federal research dollars or being done in scientist laboratories and how it might affect your lives? Not surprisingly, people overwhelmingly say yes. This is a survey from just last year, and it shows roughly 90% of people think it's somewhat important or very important that scientists communicate with the public. So the flip side of that question is, if that's why science cares about you communicating, why should you care about communicating? And I think there's a very strong argument to be made for that as well. And in my view, it's that the only value that any of our work has is the value that we succeed in communicating to other people. So we could do the most robust, accurate, effective, novel research imaginable. But if we can't successfully convey to somebody why it's important, why it's correct, and critically, why they should care about it, that work will literally have no impact in the world. It'll go unnoticed in terms of the benefit that society may extract from it. And frankly, it'll also go unnoticed in terms of the benefit that it may have to you as a scientist and to your career. So your ability to communicate, I believe, is really, really directly linked to the impact that your work will have. And the last point I want to make is about sort of who needs to be doing science communication. So looking at that survey result, I think it may be easy to assume that when people answer a question like that, they're thinking of like Stephen Hawking or Neil deGrasse Tyson. They're thinking of like the big scientists that they may know by their names. But I think that's really, whether implicitly or explicitly, I think that's not what people mean when they say that scientists need to communicate. And the reason is because of who is doing science. So the NSF publishes this great report every year, the Science and Engineering Indicator Survey, where they actually do a census, basically the scientific community in the US, especially the community that's using federal grant dollars. And they literally ask the question, who is doing science? And I think the answer is fascinating. The answer is that graduate students do science. For every faculty member that's doing research, there's roughly an order of magnitude more graduate students doing science. So the people who do science in our country and around the world, especially in academia naturally, are graduate students. So if we want to ask who's responsible and who we should be supporting and encouraging to do science communication, I think the answer has to be students, and especially graduate students. So part of the reason I feel really passionately about this is that I had the pleasure to join with a lot of my colleagues when I was a graduate student to form a great organization called ComSciCon, the Communicating Science Conference. And for all the students in the room, I want to be sure to advertise this to you and make sure you know that it's an opportunity that's available to you. So ComSciCon operates a series of science communication workshops that are free to attend for graduate students throughout the year and across the country. We have an annual flagship workshop that takes place every year since 2012, usually in Boston. And we also have a network of regional events organized by graduate students distributed throughout the country. So all of ComSciCon's events are operated by graduate students who have their sort of finger on the pulse of what skills are needed and why communication is important to graduate students. And again, they're operated on a volunteer nonprofit basis, free of charge to students. So we do have franchises throughout the country, including a franchise in Michigan and in Chicago, which I think would be the two closest ones to us here in Indiana, that have conferences on an annual basis. So if you're a graduate student and you're interested in this topic, and I hope that you are, I really encourage you to, one, check out comscicon.com to learn more, and two, please feel free to ask me if you have any questions. And our next flagship workshop will be in June next year, and the application will be up in January and February. So with that, I'll leave it there, and I want to thank you all one more time for joining for the session today. Oh, that's such a great question. I mean, it's really puts your finger on what's key to us being successful in our own business. So I think there's a bunch of different aspects to that. So one is that it's really incumbent on us, especially for those of us who are coming from different fields of science and are new to entertainment, to really build domain knowledge, to learn from experts in the field who maybe aren't taking the same perspective that we are. Maybe they're not doing their work in terms of quantitative modeling, but they have a wealth of knowledge about how the industry actually works that we need to take into account. So for example, when we're building our box office projection model, we've made an effort to incorporate some knowledge about the structure of our industry in terms of how we build that multi-level model, the grouped regularization that we do. And we couldn't do that without learning from the domain experts in the company. Secondly, we need to understand what challenges they actually are trying to solve. We need to understand their business really well. We need to integrate with them and understand what they need from us. We can't make assumptions about what type of modeling is going to be most successful for them. We need to really listen to them and learn from them. And the services team that we have in applied analytics is really designed to do that. It's designed to deeply integrate with the business leaders at our company to help us sitting in the office in Boston, who are a little bit separated from that, understand as best as possible how we can really impact them. And then the third part, I think, is building models that are interpretable and communicable. So I think not all models are created equally in terms of our ability to extract information from them and understand them. And I think it's important for us to be building models with that in mind, not only prioritizing that, but keeping in mind how we're actually going to convey the results of that modeling process and making sure that we're building models that are aligned to answering the exact questions that people are asking in the business.
Two of the ideas that I try to sell my students on, I'm looking that one, even if they become more creative, the organization would, it will still be beneficial to them to kind of understand science, element, analysis, that's going to come in because you evaluate in terms of like how you evaluate.
Yeah.
So that's true.
I think that's true. I mean, another challenge that we have is that if we're doing our jobs well, we need to be able to explain the work that we're doing. So even if we're talking to someone who has a creative background in the company who may not be familiar with a lot of the terms that we would use, we need to be able to explain exactly what they're doing to them in order to convince them that it's important and relevant for them and that it's reasonable for them to follow the guidance that's being generated from the modeling process. And so part of that is us being really successful as communicators to make sure that we can convey that information. But the job's definitely easier if we all collectively as a society have some common basis in understanding things like the scientific method and numeracy. So I think it's really critical at an educational institution to be able to prepare students with a diversity of skills, which sounds like exactly what you're doing.
I also tell them that, look, and I have a lot of job ads that have already proved it. You might not get the astrophysics and have that level of analytic capability, but there are intermediary statisticians and have a higher level of understanding. But even if they don't go on to that level of education,
I think it's absolutely true too. And when I just think of my own experience, I think part of the reason we've been successful at applied analytics is that we do have this model where we bring in a bunch of different skills. We have the services team with kind of a strategy and a business perspective. We have the quantitative team with the scientific and data science perspective. We have a software engineering team with that computer science perspective. And I think with any one of those pieces alone, even if all of us individually have, bits and pieces of those other skills, I think with just one of those resources, we wouldn't be able to have the impact in the business that we do. So I think it's really critical for those different roles to exist and for them to be married together and all treated as first-class citizens within an organization and the industry. I totally agree.
So I think the first and second question is really asking the same thing on the side. So one side is you're building a complicated model, especially now the deep learning is going like this thing. Now, how do you explain this result you get prediction from deep learning to your decision maker, which is your boss? Say, oh, I use this complicated model, I predict you should put this thing as well as this. How he can attribute that if the result is to actually make decision, because the learning that between the complex model you have or interpretable big of the model you build or especially deep learning, this is a black box.
Yeah.
And the decision maker, how do you solve this gap, communication gap?
I think it's such a great point. And to treat that in the abstract for modeling generally, I think it is a really hard challenge to be able to communicate the modeling work that we do to a variety of different audiences. And I wish I had sort of like a bag of tips and tricks to share, but I think it really just starts with understanding the importance of that task and treating that as a priority in your work, that being able to communicate the results of what you're doing is going to be a key aspect of the product that you're delivering. We always try and take that perspective. And then to go from the abstract to the specific for deep learning, I think you're right. I think the sort of the black box nature of how deep learning has been applied in the last few years, when it's had so many tremendous successes, I think does limit its applicability to certain problems. And I think a lot of the most interesting work that's being done in that area right now is on the interpretability of deep learning models, even building models that analyze the model that help us understand what each feature layer and weight is doing, so that we can better understand why the model is making the predictions that it does, and so that we can extract information that's learned by the model during the training process. And I view that as by no means a solved area, and I think that we have a lot to learn from a lot of the research that's being done there now. And I hope that that's going to be a major area of focus for the whole community going forward.
Because the interpretation of machine learning and deep learning method is big to do in the data science area. So I think there's actually in medical diagnosis, not like image diagnosis, deep learning are not normal medical diagnosis. If you use deep learning, you get a result that this person needs to take this drug. And the doctor actually cannot use this prediction because he has to explain why he needs to take this drug. And they put on model, he actually cannot explain. Basically, they couldn't use the data science method unless you are interpretable.
Yeah.
So that's the one side of communication. The other side of communication, back to the students, like the other side, there's many people working in our industry, right? And you think of data literacy, and you have all kinds of different teams because data now is everywhere. I believe that everybody should have a literacy of data, that even they are not dealing with data or building this predictive model, but they should have the literacy. I want to know in your area, independent area, what are the every staff or every people there, what kind of literacy they have to build up on the field of this job, and work with your data scientists and do communication together.
Yeah, I agree with that too. And I think We're a little bit of a unique group in our industry, our applied analytics group, because we're focus built on the idea of leveraging data in entertainment. So we have a very high level of data literacy within our group there in Boston. And part of our role is to really increase the impact of data and the literacy about data throughout the company. So to be able to work directly with stakeholders and business leaders throughout all those brands that I showed that are part of Warner Media to make sure that they're all getting as much value as they should from the data assets that we have and the investment that we've made in modeling. So yeah, I agree with you. That's really critical.
Do you teach them R and Python? Usually to have a basic understanding of R and Python,
Throughout the whole company? No, I mean, so speaking broadly about a entertainment company in general, there's such an incredible diversity of skills that need to be used to produce and distribute content. So there are people who need to be technical experts in very different domains, not in data science, but in things like content production and filming, and the kind of like audiovisual equipment that's involved with that. Who I'm sure like have all of the requisite abilities to learn the type of technical modeling that we do, but that's not what they specialize in. And we don't want to be disruptive to that work, and we don't want to be reducing the impact that they bring to the company through that set of skills. So I think it's really more important for us to, generally speaking, it's more important for us to be able to meet all of the roles in the company sort of where they are and make sure that they're getting all the value that they should from data by helping them use the tools that they already have to understand that what we're doing. I think that's the first job that we have. But I do think in general for society, raising data literacy and making sure that no matter what background people come from and work they go into, they have numeracy and the ability to interpret data and the ability to do some analysis of data themselves is very important. And I think the role that a program like this one, the data science program at IU, is playing and doing that is just crucial. Maybe in the back.
Right now we talked about the box, but I wanted to do the inclusion also concentrate on the post-release situation, like after the movie is out of theaters and goes into private. Yeah. So do you like also study that how it has accepted by the consumer and what factors the factors change, right?
That's such a great question. The answer is yes. So after release, the first decision that's made, basically, like literally the day after the movie comes out, is are we going to spend money on what's called chase? So now the movie's out in the box office, are we going to continue spending money on advertising it? Or are we just going to pull up the rug and stop spending money on it and let the things take its course? And believe it or not, that second thing of just not spending after release is the default. That's what most studios and most films do. So you might notice that after most films are out, you stop seeing advertisements for them. But of course, there's also an opportunity to benefit and to boost future box office performance. And the day the movie's released, the day we get that first signal from the box office about how many people are actually going to see it, we have dramatically more information about the film than we do before. So the first thing we do is box office modeling for chase to say what's going to be the impact of an additional marginal dollar spent on advertising. Then home entertainment is, the revenue is not quite as high in general as the revenue from theatrical, but it's close to it. It's a similar magnitude. So modeling that domain is very important also. And I just realized I
just want to ask a question for a student who could talk about.
Yes. Thank you for reminding me. I forgot to mention that we do have internship opportunities at Applied Analytics. I want to make sure that you're all aware. So we do offer a summer internship. We're a relatively small group there in Boston, so we typically just have a few summer interns per year. But if that's something interesting to you, and if you'd like to check out the Copley Square neighborhood in Boston and join our team, please feel free to reach out to me. I've left my contact information with the department, and I'd love to follow up with you to have a chat and definitely to talk with you if you'd be interested in the summer internship. We also do something that we call a graduate research fellowship, which is basically a side project that you would do during your degree program. Often we're working with PhD students who are basically doing like a side chapter for their thesis that ends up being in entertainment. We give them access to data, computing resources, and projects. And we encourage them to publish that work when they're done or to put it as a chapter in their thesis. And of course, it's a paid position, so there's that benefit. And then we also want to learn from someone who's really a world expert in something, someone who's doing really novel research in an area that's not part of our skill set yet. So if you're interested in either of those opportunities, I really encourage you to reach out. I'd be glad to chat.
Okay.
Thank you.
It's a very nice talk.
Thank you so much.
again for coming over.
Oh, it's really been a
Nice
pleasure.
to- Yeah, I think you guys will do really interesting. Hope you enjoy. When are you coming back? When are you going back?
Tomorrow morning.
Okay.